Okay, so today we're going to talk about what's called sampling variability with proportions. Again, just looking to see how much, when we have a proportion, our samples vary, and also learning about what's called margin of error and 95% confidence intervals. You're hearing an awful lot about margin of error in the news these days with the presidential elections, and so now hopefully you'll get a good sense of what that really means and what they're talking about. Okay, so in terms of our notes, by now we've noticed that proportions vary from sample to sample. Even with data as simple as our bags of M&Ms, few of us had the same proportion of, say, orange M&Ms in our bags, or any other color for that matter. Hopefully you've also noticed that as we increase our sample size, the variability in the distribution decreases. So the more we looked at our M&Ms and the more we plotted all the points and counts, the less variable that data was, the more consistent it was. And it becomes approximately normal. And that's why we talked last week about our normal model. You should also be convinced by now that we can never really know about a population. The best we can do is draw many different random samples. Very much like we did in class today. But now, tonight, we can learn how to more accurately measure how confident we are in our prediction of what's happening in the population based on our sample proportion. So we're going to be making some more accurate predictions. On the next page. For random samples of size n, the standard deviation can be calculated using the following formula. Standard deviation is equal to the square root of the proportion that we know times 1 minus that proportion over the square root of n, where p, again, is the value of the population proportion and n is the sample size. Be aware, sometimes you'll see this written as the square root of pq over n, but that's just because as we do more probability and statistics in later courses, q is implied to be 1 minus p. I'll try to remember to always write it this way, but sometimes you'll see me writing Q, and that's why. Okay, let's do some example problems. Mars Corporation claims that the proportion of orange M&Ms is 0.2. We took 25 samples between the two classes. Let's find the standard deviation. So just practicing that formula. So our standard deviation will be the square root of the proportion of M&Ms we're told are orange, 0.20, times 1 minus that, which is 0.80. So these two numbers in the numerator always add up to 1, and we'll divide that by our sample size. So this is a real quick calculator process. And remember, your calculator will do everything for you in one big step if you know how to use it. So please make sure you're doing that. Otherwise, you can run into PEMDAS mistakes, and that's the worst thing ever because your calculator takes care of it for you. There's no reason for PEMDAS mistakes at this point. And there we have our standard deviation of 0.08. Okay, let's do one more and see what happens when we increase the sample size. So same M&Ms, so the company says that the proportion of orange is 0.2, but we're going to increase our sample size to 50. So here our standard deviation will still be the square root of 0.20 times 0.80, but now we divide by 50. See what's going to increase, what's going to happen to our standard deviation as we increase our sample size. This is a super quick calculator move if you remember about editing. And now our standard deviation is 0.057 or so. So you should notice once again that when I increase my sample size from 25 to 50 M&Ms, my standard deviation, which is a measure of variance, decreased. So on the next page of your notes, sample size increases, variability decreases. That is a common theme. Math is consistent. In general, for a known population proportion, like the proportion of orange M&Ms, about 90% of the outcomes of a sampling distribution will fall within 2 standard deviations of the mean. So again, they tell me that there's about 20% orange M&Ms. We take lots of different samples, and about 95% of the time, our sample proportion will lie within 2 standard deviations of the mean number of orange M&Ms. But what you have to remember is that sometimes strange things happen. And in this case, if we're doing a 95% confidence, then about 5% of the time we'll miss. And we won't get nearly as many orange M&Ms as we thought we should have, or we'll get way more in a bag than we thought we should have. That happens occasionally. But again, we're talking about a 95% confidence. So most of the time, 95% of the time, our samples will lie within about 2 standard deviations of the mean. When we estimate that population proportion, we have what's called a margin of error. There's going to be times when we don't get it right. And in fact, it's 5% of the time when we're talking about a confidence interval. So the way we define margin of error, a couple different ways, is this. It is the maximum expected difference between the value of the population proportion and a sample estimate of that proportion. Another way of thinking about or defining margin of error is the farthest away from the actual population value that you think your estimate is likely to be. So how far do we think our estimate from the true proportion is likely to be? Think about what you hear in the elections. The latest poll I think I heard was that in New Hampshire, Bernie Sanders and Hillary Clinton are in a dead heat. They're in a tie, essentially, because maybe it was Iowa, doesn't matter, because Bernie Sanders has, I don't know the numbers, 47% of the vote, and Hillary Clinton has 49% of the vote, but the margin of error is plus or minus 4 percentage points. So what that means is they think that their estimates are pretty accurate within about 4 percentage points. So if you add 4 percentage points to Bernie, he catches up with Hillary, or subtract 4 percentage points from Hillary and she falls behind Bernie. And so it kind of gives wiggle room. And there's math involved and there's a formula involved. And this isn't as precise of a formula as they use in real statistics or in polling, but it's what all you need to understand in terms of an Algebra 2 statistics margin of error question. The way we will find margin of error in this class is it'll be 2 times your standard deviation. That should make some sense because remember our normal model, when we go out 2 standard deviations from the mean, that's about 95% of our data. That's why we call it a 95% confidence interval. That's why we multiply by 2 to get both ends. So it's 2 times our standard deviation. And if we're talking about how we estimate our proportion, we're going to say p hat times 1 minus p hat. Our proportion estimate minus 1 minus it, or times 1 minus it, over that sample size. Okay, so you do need to know that margin of error formula, and we're just going to practice it some now. So again, let's think about our M&Ms. We're going to find sample proportion of successes and the estimated margin of error for each of these situations. So let's say we take 20 M&Ms and we get 5. Okay, well, our proportion is that 5 out of 20, or 5 M&Ms out of 20, and that's 0.25, which means our margin of error for that proportion will be 2 times the square root of 0.25 times 1 minus that, or 0.75, over my sample size of 20. Again, quick calculator work. Our square root of the fraction 0.25 times 0.75 over my sample size of 20. And we get 0.194 or so. 94. Okay. The only difference in these formulas is to adjust our sample size. So here I have a sample size of 40, and I get 10 red M&Ms. Well, my proportion then is 10 out of 40, which is also 0.25. So my proportion stays the same even though I drew more M&Ms total. My margin of error now will be 2 times the square root of our proportion, 0.25, times 1 minus that, 0.75, over my sample size, which is now 40. Again, quick calculator work. Sorry, I don't know how to make that mark go away. Work, just edit our last setup and change that denominator to 40. And there's our new margin of error. Okay. So what I'd like you to do now is try 3 and 4 on your own. Pause the video, try it, and then check your answer against mine. Okay, so once again, you should be noticing with our math is consistent that as we increase our sample size, the margin of error decreases. Our margin of error keeps going down as we keep increasing our sample size. Margin of error is another measure of variability. So it should make sense then that as I increase sample size, our margin of error decreases. Math is consistent. So the last thing I need you to do today, and I'm going to talk about it briefly in the video and we'll do much more with it in class tomorrow, is really, who cares? Like, when am I going to do this? What is this really telling me? Well, let's use our numbers from number 4 above and think about this. Since our margin of error is 0.087 and I had a proportion of 0.25, I would say something like this. Given many different samples of size 100. So if I took lots and lots and lots and lots and lots of samples of M&Ms and each sample had 100 in it, I am 95% confident. Why 95%? Well, because I'm going 2 standard deviations out from that mean on my normal model. And since my sample size is getting larger, I'm getting more normal. So I'm 95% confident that the true proportion of red M&Ms is between, well, I'm going to take my proportion that I found in my sample each time, 0.25, and I'm going to subtract my margin of error from it, 0.087, and I'm going to add my margin of it, 0.087. When I do that, I get 0.163 and 0.337. So again, when I do find my margin of errors using my 95% confidence interval, I can say something like, given many different samples of size 100, I'm 95% confident that the true proportion of red M&Ms is between 0.163 and 0.337, or between 16% or so and 34% or so, if you choose to round that way. So, we will be doing much more with confidence intervals in class. Just wanted to give you the mechanics of the formulas and one example of what it means using our M&M data that we took in class. And we'll do more together tomorrow. Have a great night.